So if everyone can take a seat, we can get started with the next session, which is the slow folks. The Susan Weifels likes to say the slow manifold of the global ocean here. But I can't say it with her accent quite as well. But so it is my pleasure to welcome you all to the next session today, which is again on these slow processes that large scale patterns over century scales. And we've got two speakers. And the first is Gebbie, who will be talking to us today about signs of disequilibrium in the deep and abyssal circulations of seawater and tracers. So Jake, welcome. Thank you.
Thanks, Charlie. Thanks, everyone. I hope you can hear me. Hi to everyone that's in the room. Hi to everyone that's online. Thanks for tuning in. I'm going to talk to you today about signs of disequilibrium in deep and abyssal circulations. And slow, I've taken it to mean kind of a decade or longer or so. If you really want to know what the talk is about, though, don't go to my original title. It's really about determining pathways from observations, trying to do as much as we can from the data, and using a little bit of inverse methods as well. So before I get started, thanks a lot, Jinfeng, for the invitation. Appreciate it. Thanks, Alyssa, for all the organization and emails. Okay, so this work primarily has been done by former students and postdocs, Eileen Bragstad, Laura Cimoli, who's going to be giving a talk next, and Zabir Davila. So thanks to them. I'd like to highlight their work. Let's see, so I probably should have figured out how to go forward, but simply use my finger. Clicker.
Yep, and it's a big button.
Great, thanks so much. Okay, so I've got 20 minutes. I'm going to give you 3 examples today. And these examples are going to answer 3 questions. Can tracer observations constrain the pathways of deep water formation and provide an independent check on dynamical models? And then how is pathway information that we're interested in here, how does it relate to the climate problem or the larger scale problem that we were charged with studying? And finally, are existing observations sufficient for distinguishing the baseline versus changes in circulation? If we don't know the baseline, we don't have a way to really figure out how climate is changing things, of course. So let's start off with number 1. What can we do with tracer observations? Okay, let's start with maybe posing a question. What are pathways? We've heard about a lot of different pathways here today or over the course of this workshop. So for example, we had pathways which were ways that a particular process affects another process. So kind of conceptual pathways was one. We have physical pathways. So how does stuff get from one place to another? And often those kinds of pathways, I would say we see arrows drawn, maybe they're advective pathways, streamlines, trajectories, and so on. However, I think it's worthwhile thinking of pathways more generally. And so these pictures from paper from Greg Johnson in 2008, they're giving us sections through the Western Pacific, and it's the fraction of water either from North Atlantic deep water in the top panel or Antarctic bottom water in the bottom panel. The fraction is telling us that there was some source of these waters and they've arrived at some destination. We don't have arrows connecting them, but our eyes are sort of bringing us from high concentration to low concentration. And this is really, this information is a little bit more directly derived from observations, and yet it's already giving us something indirect about pathways. There's some problems with that, of course. So this water mass decomposition, you basically give it some source values for your water. They don't necessarily correspond to any particular place in the ocean. They're just something when we look at observations that seem to give us some extreme values that are representative. And then if you do this with real data, you might not get coherent pathways. You might get blobs or inhomogeneities. You might not be able to visually draw a line. Okay, so for the first example, let's take a look at the relatively well-observed Nordic seas, and where on the left-hand top left panel, we have the observations of temperature and salinity over the last couple of decades. So it's 2000 to present. And in the top right panel, we've got oxygen and nutrients. So it's a relatively well-observed region of the ocean. You can also take a look at the histograms in the bottom that we've got good seasonal coverage. We've got coverage over actually 6 decades, 7 decades or so. It goes back even farther than that. So in this work, Eileen Bragstad has applied essentially an extension of water mass decompositions. Here I'm referring to it as TMI. That's total matrix intercomparison, but it's really, there's too much information going on here. So a TMI is an easy way to remember that. That's the secret of acronyms, right? You just have to remember them, basically. Okay, so she's applied this extended water mass decomposition method, which just adds really one thing: take geometric constraints into account. So you need, if you have, say, North Atlantic water showing up in a particular site, what this method does is it needs to find basically a coherent plume of that water all the way back to the source. So for most of this talk, I will consider that as not having a model, but that's not quite true, right? There's no dynamical model here. There's this simple connectivity model. And if you write down the equations, it's actually consistent with having a statistically steady circulation. So that's an equivalent assumption here, which we know is not valid, strictly speaking. Okay, if we take just temperature, salinity, oxygen, nutrients, add geometric constraints to them, it permits the contributions of waters that really aren't coming from places that are all that different from each other. So in this case, the bottom left-hand panel is showing different regions in the Nordic Seas. We've got black lines that are distinguishing different surface patches. And so instead of defining things just as source properties, instead we're defining waters as coming from a particular place. So they have an actual source location. We've got Greenland Sea, Iceland Sea, Atlantic Domain, and so on. When you do that and impose the fact that there must be coherent plumes if you're in a steady circulation, then you can get the heat maps on the right-hand side. And those are sections across the Denmark Strait. So Denmark Strait between Greenland and Iceland, seal depth 630 meters or so. Super important site for slow pathways in the ocean, because this is going to be one of 2 or 3 major ways that Nordic Sea's water can get everywhere else in the world ocean. Get interesting maps where things like Greenland sea water is the densest, and sure enough, the heat map there says that in the bottom part of the Denmark Strait, that's where the Greenland sea water resides. So even though we didn't tell it anything about, say, gravitational stability, the observations are enough to give us that constraint. Okay, we can see more in this as well. We have, say, warmer waters that have come in from the North Atlantic Current, Norwegian Current. They're from the Atlantic Domain, or North Atlantic in this case, and they occupy kind of higher up in the water column. Okay, so this is fine, but what does it have to do with pathways? Well, it turns out you can basically figure out these water mass fractions in different places, but you can actually treat it like a model here. You can say, well, what if we just have a tracer dye that, let's dye the surface of the Nordic Seas, value of 1. You can find out where the water goes. And this is without any model, without any dynamical model, I should say. It's from the same analysis. So there's 2 cases here. On the right-hand side, we've got a black box up near Svalbard. And we just dyed that box, and you can see the pathway of the East Greenland Current coming all the way down towards the Denmark Strait. Fairly highly resolved, even, just from observations. The one on the left here is interesting. There's no reason why time has to go forward. And what if we dye a gateway at the Denmark Strait and ask, where did the water come from, instead of where is it going? Get some very interesting things. It's not just the East Greenland Current that matters, but there's a pathway that goes close to Jan Mayen in the center of the Nordic Seas. It's clear if you look at Iceland, Scotland, or at Barrow Bank Channel overflow water. There's basically an offshore pathway, offshore of Greenland. This pathway actually goes through a couple fracture zones near Jan Mayen. So a connection between the Greenland Sea and Iceland Sea, which was previously unrecognized before this analysis. And consequently, Eileen has gone out on a cruise, deployed gliders in the region, and confirmed that there is significant flow. Okay, this is all great. We can get pathways. It looks like we know a lot, but I'd like to tell you about also what we don't know, what the challenges are here. In this case, the answer she gets depends on whether she uses data post-2000 or pre-2000. In the analysis that I've shown you here, post-2000, she finds at certain depths there's a lot of Arctic water. that coming through the northern boundary. I don't think we can take it at face value, actually. So what's happened is Greenland Sea deep water doesn't form as deep as it used to. And there's waters in the deep basin here that can be explained by no steady circulation. Their connection to the surface is a relic at this point. It no longer exists. Turns out Arctic water has about the same properties as it, because those Arctic properties are actually were Greenland Sea deep water from 100 years ago or 200 years ago. So it's signs that there's disequilibrium in the ocean that we would need to take into account if we'd want to accurately interpret what's going on. So don't be fooled by how certain this looks. Okay, so let's go to question number 2. Okay, how is pathway information related to global quantities of interest? Well, let's take the same kind of analysis, which I call TMI, but apply it to the global ocean. So it's going to be at more coarse resolution, 2 degree by 2 degree horizontal resolution, about 33 vertical levels. So we've used a climatological atlas of data. We've got temperature, salinity, oxygen, phosphate nitrate. We've got oxygen isotope ratios in there as well. And the first question is, well, really, does this work using just observations at a global scale? And so to convince you that not necessarily that it works, but that it gives the same answers as using either a dynamical model or using an inverse method, in this case from De Vries and Primo, that includes observations and dynamics. I've plotted this for you. So these are different sections, in this case, the Atlantic Ocean. And instead of, it's similar to the heat diagram I showed you before, but in this case, it's the green colors on here are showing high concentrations of water. And so the left-hand column is going to be this kind of observations only, extended water mass decomposition method. The center column on there is the OCIM, De Vries and Primo. And then the far right-hand column is a NEMO dynamical model. Looking at how much Antarctic bottom water, Antarctic intermediate water, and North Atlantic deep water are there, we see similar pathways. If you take a closer look at it, you'll see that the observation-only method appears to be a little bit more diffuse than the other ones. Okay, so it seems like we can apply a similar method to the global ocean. Here's the innovation of this part. If you take that pathway information, pathways I'm taking here to be synonymous with how much water exists in different parts of the ocean, and then just add rate information. In this case, it's rate information from radiocarbon, so radiocarbon of DIC. It permits construction of an empirical ocean model. It's actually enough information to figure out both where water is going and how long it takes to get there. So the pathways part is basically, I'm including advective and diffusive processes. You might consider that just the unresolved advective processes as well. And then rate information. And you can come up with, in this case, it's an age distribution at 2.5 kilometers depth. So definitely talking deep ocean for this audience here. It's the mean age in this case. So age distribution is a recognition of the fact that in any parcel of water, some of it got there fast, some got there slow. Mean will be looking at that distribution and taking the center of mass of it. And this is a slow circulation for sure. I don't have a pointer, but you can see in the Pacific Ocean on the right, we've got mean ages about 1,200 years or so in the North Pacific. Okay, so what can you do with pathways and rate information? Well, I can indulge myself here for 1 second with an aside. We often talk about sources of water, like locations where they come from, but we could think about their temporal location that they came from. When were they last at the surface? And we could plot something orthogonal to the previous plots. So this is 3.5 kilometers depth, Pacific Ocean mostly. This is from Jenkins et al. 2024. Can actually plot the vintages of seawater. Vintages here, thinking of your favorite vintner coming out with the 1996 Chateau Lafite Rothschild. But here we've got the Roman warm period vintage in the deep Pacific, chilled for your pleasure. And then you can look at newer water, Little Ice Age water from 200 to 600 years ago. It's more predominant in the South Pacific Ocean. This is the conveyor belt for you. That, you know, there is no conveyor belt, right? But that is a simple explanation of what you see here. That was my aside. Okay, what was the point? What can you do about global metrics like climate? Well, if you have boundary conditions, say you have sea surface temperature, you need it over the 20th century or over the modern warm period, or let's say you have PCO2 in the atmosphere, you can use this simple empirical model with those boundary conditions, run it forward in time. And on the left-hand side, so we've got ocean heat uptake in the upper 2 kilometers. Right-hand side, we've got anthropogenic carbon uptake. And so using my simple method, it shows up as the red curve on the left-hand side, and it's the solid black curve on the right-hand side. You can compare it to lots of other ways that these quantities have been computed, and you actually, amazingly, get something very, very similar. Does that mean we should throw out the complicated models? No, no, we shouldn't. What this means is it's actually a sign that most of the signal that we're seeing can be explained by the propagation of anomalies along the existing pathways. That's how important getting these baseline pathways are. There's lots of reasons. Just because all of these things are alike doesn't mean any one of them is right. Okay, so they're all missing some of the same processes. So let's not be too confident. Okay, there's also other issues. So let's say I do something simple. I've got this empirical ocean model. I just give it sea surface temperature over time, which we don't even know very well. And we look at, how much does temperature change from 1875 to 1995? Get interesting things like actually a little bit of cooling with the blue colors in the Pacific. That's a reflection of pre-industrial variability. It shows up in some ocean reanalyses, but it doesn't show up in others. So whether that's real or not is unclear. An issue is if I replotted this at the seafloor, you'd see roughly the same plot. But we know, Perky and Johnson, 2010, 2012, work by Damien Desbruyere, that there is warming along the seafloor, especially in the Southern Ocean. A tempting hypothesis here is that this model is still useful for telling us that there is no way with a steady circulation to explain the warming along the seafloor, hence implying that the warming is an indication of circulation change. And that's a hypothesis that I favor myself, but unknown if that's true or not. Okay, let's, in the last couple minutes here, let me tell you about our existing observations sufficient to really tell what's the steady circulation and what are the changes in the circulation. Everything I've shown you so far with radiocarbon, with background temperature and salinity fields, I don't think it's sufficient to get the rate information. So we've got errors 20 or 30 per mil on radiocarbon. It's got a 5,730-year half-life. It just doesn't have the precision. So we need something else. Here, this is work by Laura Cimoli, and it's atmospheric CFCs in sulfur hexafluoride, and roughly inert or passive in the ocean, but they have different surface time series in the top middle panel. So they're basically giving us different signatures or imprints in the ocean, and they're acting on their surface history has like a 70-year time frame to it. So complementary and a faster time scale than what the radiocarbon gave. What Laura's done, look to see, can you use the simple TMI method to reconstruct all the observations from GLODAP, including others from Arnold Gordon and Hood et al. In 2010? The answer was no. Lots of places you can do well, but if you look in the Southern Ocean, so you can do very well, and here's reconstructions of CFCs in different sections. This one happens to be Pacific on the left, Atlantic on the right. These maps look plausible. But then when you take a closer look, they even give us some information. Let me tell you the positive parts of the study first. So if you can look at things like arrival time of the CFCs at the seafloor, and you can get a sense just by looking at how aging occurs and draw pathways on that. And you can get more detail then about just exactly how does Antarctic bottom water, say from the Ross Sea or the Weddell Sea, how do they take different pathways in the world ocean? If you look quite close though, there's misfits between taking the kind of simple approach and fitting the data. And the misfits predominantly here are outside the Ross Sea sector. So you see the Ross Sea in the top right. You've got these red blobs at the bottom. So it's basically meaning the reconstructed time mean circulation is slower than the observed one. So the CFCs, for the most part, are monotonically increasing. So if the value is too high, you get a sense that the circulation is either too fast or too slow. So this is very interesting. You might ask, is it just outside the Ross Sea? It turns out if you follow the baseline pathway of Ross Sea abyssal water into the basically south of Australia, you see similar blue and red blobs down at the seafloor. So similar misfits. So it's saying the signal is not just confined to the Ross Sea, but it's downstream as well. One other thing to notice is that the anomaly in time, 1995, the anomaly here was blue, and then it turned to red. So that's an interesting clue. And it turns out, I'll give you the answer here. If you have a circulation that's slowing down in time, then you would expect the CFC, and then you tried to fit it with a steady circulation, what you're going to get is a misfit of one sign early on in your record and a misfit of the opposite sign later on. I tried a one-dimensional pipe model here to see if that would work. The left-hand side basically says, you know, on the pipe, we've got a increasing concentration of CFCs, linearly increasing. All the different curves to the right of my one-to-one line, those are different, what we would expect to observe of CFCs in the interior ocean under different circulation speed-ups or slowdowns. So if the circulation is slowing down, then the CFCs stop increasing. But if the circulation is speeding up, then the CFCs are slow and then they ramp up quickly. What's on the right-hand side is taking the same plot from the left-hand side, but seeing what is the error. So what is the difference between what you would get for a steady circulation versus one where it's changing? And the idea here is in time that we have errors of one sign early on and the opposite sign later on. And so from this, you can actually try to figure out what the circulation slowdown was based on the observations. Okay, so the summary here. First, lots of different ways to define pathways. I picked kind of a general one here that I hope you found useful, and it's a tracer-centric definition. In the Nordic seas, I mean, we can really do a great job getting the details of pathways, but we already see signs of circulation change going on that we need to take into account better in the future. Pathways plus rates, that's an ocean circulation model for you right there. It's empirical, so you could independently compare it to dynamical models. Another reason why you might want an observation-only model is so the biases in models don't get into your estimate. That being said, the right thing to usually do is use all the information when you're making an estimate. I do agree with that. Okay, so transient tracers and biogeochemical properties. Getting out rate information, lots of which we've heard about earlier today, or using CFCs that have complementary rate to radiocarbon or longer rates. That's the way to go to improve this analysis. So, thanks a lot.
Thanks, Jake. And Jake will be back for questions after our second talk of this session, which is from Laura Cimoli from the University of Cambridge, who will talk to us about fast to slow impacts of turbulent mixing. So I believe Laura's remote.
Yes, thank you so much for having me. Sorry, I couldn't be there in person. So this talk is going to focus on the pathways that are regulated by turbulent mixing. And so I will give a brief overview of what is mixing, mostly because of the also multidisciplinary audience that we have. And then the talk will discuss like 3 different ways mixing can affect either the circulations or the tracers that are carried by the circulation on very different time scales. Actually, I know this is the slow pathways, but I think some of these are definitely slow, in particular in relation on the role of mixing and the regulation, how it regulates the MOC, the meridional overturner circulation on centennial to millennium timescales. But then I also want to talk about mixing and its role in regulating the tracer distributions, both the tracers that can be carried by the MOC, but this can be on a shorter timescales. It doesn't necessarily be on the timescale of equilibration timescale, for example, of a MOC, as well as like how it could actually affect some biogeochemical processes on much shorter timescales. And I hope you can see my cursors because I'll point to things. You can also just nod in the room. I guess I can see you if that's the case. So first thing is what is really turbulent mixing? And that's like the process of, if you wish, of, I mean, there are many definitions, but one is if you can think about it as the process that leads to the homogenizations of properties due to the turbulence that is generated by the breaking of internal waves. So in a stratified flow, like the oceans, could be really zoo of processes, which are shown in this schematic here on the left, that can lead to the formation of internal waves. Those waves can then grow, especially as the ones we see on the shore, and they can break, and that breaking leads to turbulence, and that turbulence can lead to the mixing of properties, or if you wish, if there was a gradient, that gradient will be eroded, so the properties will be homogenized. So you can think about water masses with different densities, which could be mixed, which means that we will lead to a transformations of water masses, or it can just act also on, for example, homogenizing like the concentration of a traces such as nutrients, oxygen, and so on. Turbulence is enhanced at the surface due to like wind-driven turbulence, as well as close to the topography, where the interaction of a flow with topography can lead both to the generation and breaking of waves. But in general, it's a highly intermittent in space and process, both in time and in space. And it is a very small scale process in the sense that really this homogenization can happen at meter to centimeter scale. So it's really difficult to both observe mixing as well as to model it. But despite this small scale, it can really have global implications, which is what I'll discuss in the rest of the talk, starting with really how it contributes to regulate the strength of the MOC, particularly of the lower limb, so in terms of Antarctic bottom waters. So the panel on the left shows the stream function. This is from an inverse model of Lumpkin and Spear in 2007. And so in blue and red, we have the two main overturning cells of the global MOC. This is shown in density space in the top and in pressure space in the bottom panel. But yeah, so the main point is really that we know the mixing plays a crucial role in setting the strength of the lower limb of the MOC. And this is, again, we're much further away from surface processes, so surface buoyancy fluxes or the effect of wind. And so mixing becomes really leading order importance in allowing these dense waters to basically be transformed through mixing into lighter water masses, and so come back to shallower depths, and then from there they can be brought back to the surface. And it can, when you look at it, the separations between the two main overturning cells, so again, sorry, I should have said it, but in blue we have a lower limb and with red like the upper one. Hope it's clear. But yeah, so the interface in density space, these two overturning cells, you can see spans several density levels, which indeed showing that there is a lot of diapiclan mixing happening between these two overturning cells. And this thick gray line here shows the mean depth of the ridges, again highlighting that a lot of this transformation really happens through topographically induced like turbulence. And this process is particularly important when we look at like the Pacific and Indian deep waters, so where we don't really have like a significant formation of deep waters in the north. And it's really thanks to the diapiclan mixing that, so that is the process that really allows the transformation of Antarctic bottom waters into lighter ones. And that leads to the formation of Pacific deep waters and Indian deep waters, but then they can make their way back to the Southern Ocean. And so the main point is really like, yeah, I mean, in this case, diapiclan mixing really plays a key role on regulating the strength of the lower limb, in particular in the Indian Pacific Ocean on centennial to millennium timescales. And if you wish to like quote and really mention book like Abyssal Recipe 2 paper is without mixing, the ocean would turn in a few thousand years into a stagnant pool of cold, salty water. And to dig a bit more into details about really how mixing actually transforms Antarctic bottom waters into lighter water masses. These are the results from a paper that came out by Lois Baker and collaborators in last year. And so they use a very high resolution numerical simulations of the Drake Passage to really look at the transformation of Antarctic bottom waters. So the panel here in the left shows vertical vorticity. So here you have the tip of South Americans, and so the ACC flows is in this direction. You can see, I mean, the models, again, is very high resolution, both horizontally as well as in the vertical. So you see a lot of features, you see eddies. You can see the model somewhat also resolves internal waves, so they're breaking and both horizontal and vertical displacements. And so one of the points of this paper, they really show that a lot of the transformation of Antarctic bottom waters really happens in close proximity with topography. So they really like emphasize the importance of topographical induced mixing. And the second thing that they highlight is that a lot of this transformation really actually happens in at very sharp interfaces between different water masses, in particular between Antarctic bottom waters and the lighter circumpolar deep waters. And so what you see in the 4 panels here is, this is for the different properties, but what I want to highlight is really the interface between Antarctic bottom waters and the waters above. So this is shown in, well, density, temperature, salinity, but these sharp interfaces are mostly evident when you look at stratification, which is the bottom panel here, and very indicated by these white arrows. And so this is important because the point is these interfaces can modulate mixing. They can either suppress mixing if the stratification is too strong, or they can create patches of very high shear where mixing is enhanced. And so they really can modulate how much Antarctic bottom waters is being transformed and where it is being transformed, so making it much more, again, intermittent phenomena. And of course, like none of the climate models have a resolution to resolve these processes, but we do see these interfaces also in observations. And again, it's a missing kind of piece of a puzzle where, while models generally have a much like broader diffusivity, rather than, again, this more like a patchy, but like of high intensity, like turbulence. And then on that point in time, so understand really in general, in more details, how Antarctic bottom waters are being transformed, and so how the pathways changes from abyssal waters to shallower depths. Again, I mean, we often think about the net transformation of Antarctic bottom waters, but in reality, there could be different patterns of upwelling and downwelling, where upwelling means that water are transformed from dense to light, and downwelling means the opposite. So waters are transformed from light to dense. And so starting with the schematic here in the middle, we know, for example, that when we have rough topography, mixing is a turbulence, is bottom enhanced, which means that the water parcel in the interior will tend to mix more with the denser water below than with the lighter waters above, and so will tend in the net to become denser and sink. And vice versa, when we're close to the boundary, we have no flux boundary conditions, so the water parcel will just mix with the lighter waters above and upwell. And so we end up with these opposed patterns of along boundaries upwelling and interior sinking, which is what is shown in these 2 panels here on the left. They show the dipycnal velocities, which is so this is inferred from the turbulence generated by internal tides. So dipycnal velocity, so it's a cross density velocities in positive indicates upwelling and negative downwelling. As if you look at the section, which is this bottom panel here, indeed you see that there is like a long boundary upwelling and downwelling just above. And so what this means really for when we think about, again, so how much in the net are Antarctic bottom waters being upwelled, we need to then calculate like an integrate of like the dipycnal velocity on different density levels, which is what is shown in this panel here. This is calculated for different density level in the Atlantic Ocean only. And so what you see in there is that for different density level, this is the integral of the dipycnal velocities, and in red, the red bars show the contribution of a long boundary upwelling, and the blue bars show the contribution of interior downwelling, and the black is the residual of the 2. So the main point is that, for example, when we look at the density classes for Antarctic bottom waters, so around 28.15, for example, in the Atlantic, you can see a maximum transport of about 5 sverdrups, but that's the net contribution of 2 much larger, so that's a residual of these 2 much larger contributions. And this is, of course, well, this is a like 1D like assumption. So what's a 1D model? Of course, we need to take into account that there is a lot of horizontal motions as well, but it's still important to take, again, when we think about how much mixing really moves the things and how much it contributes to changing the pathways of water masses and also the tracers that these water masses carry. And one last thing quickly, actually, on this topic is there was actually a recent field work that really was the first like observational proof of this along boundary upwelling. This was the boundary layer turbulence project. And so what they did is, well, among other things, is that they injected a dye in this trough area. This is a Rockall trough, which is trough just off the coast of Ireland, and where there is a lot of turbulence regulated by internal tides. So we injected the dye just 10 meters above the seafloor and then monitor its evolution as it was like being mixed and moved around. And so this panel here, the panel D here, is a temperature salinity plot, which shows the evolution of a center of mass of a dye as a function of time. So the colors indicate time, the circles is the center of mass, and the size indicates the concentration. And so what it shows is that from the moment of injection, which was at the start here, the concentration will decreases as it is diluted over time. But the main thing is that as the time increases, the center of mass moves diagonally, so it moves like towards lighter density levels. So indeed, this is showing that there is a net along boundary upwelling, which was also confirmed like by realistic numerical simulations in that area, where indeed they showed that if you injected the dye in very close to the bottom, the center of mass would in the net upwell, and vice versa. If the dye was going to be injected higher up, we would experience a net downwelling. And so just a quick recap of this was the first really observational evidence of this more theoretical, if you wish, 1D framework of along boundary upwelling and interior downwelling, which is an important aspect to take into account when we think about in the net how much mixing really contributes to set the pathways of Antarctic bottom waters and how they basically are being brought back up, and so really regulating the strength of the lower limb of the circulation. So now switching a bit gear, I wanted to talk about also how mixing affects the distribution of tracers as they are carried around by the MOC, with an example from the Atlantic Ocean. So in these examples, like start with a schematic, like think about a tracer that is sequestered, like taken up by North Atlantic deep waters and carried in the interior. And from there it's carried southward towards the Southern Ocean. And so really the question we wanted to answer was how much that mixing can move these traces along the way. And this is important in the sense that we're not talking about how mixing affects the tracer distribution through changes in the circulation, but is really directly acting on the tracer gradient. And so it's acting on much shorter timescales than the equilibration timescale of the AMOC. And so we calculated these diffusive length scales using different observation-based mixing estimates, which is what is shown here. The main point is that this diffusive length scale can be very large, of the order of like hundreds of meters up to like 1 kilometer. So it is a significant displacement. And this is important because, of course, it means that mixing can exchange with tracers along the way across different water masses, but also it can really change where this tracer will upwell in the Southern Ocean. Because like lighter water masses would tend to upwell farther north, and then from there could be transformed into lighter water masses and make their way back northward, while denser water masses like can upwell further south and be transformed into Antarctic bottom waters. And so if you think about how the signal, for example, of anthropogenic heat or anthropogenic carbon that are being sequestered in the North Atlantic and they're being carried south, again, we want to really know how much of the mixing they can experience along the way and whether this could affect like where their outcropping point in the Southern Hemisphere. And the last bit is like still tracer related, but I call it like a BGC, like in terms of biogeochemical processes, because it's really more focusing on how mixing can affect biogeochemical processes, but on much faster timescales. Because we often think again about, so this is going to be more like, if you wish, like fast pathways, because it's not related to so if mixing, of course, can alter tracer distribution by changing the circulation, but that of course will happen on centennial to millennium timescales. But the main point here is that even it can act on the tracer gradient on much faster timescales. And so, for example, like resupplying nutrients in area that could be nutrient depleted. And in that case, like the response of the system could be like anywhere from annual to decadal or longer. And these are two examples. So this was work led by Elizabeth Ellison. She started with a very idealized numerical simulation. So this is like a 2D zonally average model. And what she did was she altered like the mixing parameters only in the South Ocean channel, which means we know it's an area where it would not really change significantly the circulation in the rest of the globe. So the overturning circulation in different simulation is pretty much the same. But what different mixing parameters do is that they change really how much the nutrients is being exchanged, because there is a gradient in the nutrient concentration, which is the green contours here. And so, for example, yeah, we supply like more nutrients to the nutrient depleted areas, for example. And then she tested really these hypotheses in a more realistic configurations, which is with the VB-SOSI, the biological South Ocean state estimate. And she found out again the change in the mixing parameters in the South Ocean in this state estimate. Again, the circulation per se doesn't change much. In general, many of these changes that she observes are so quickly that they're not really related to, again, the equilibration timescale of the circulation. So what she finds is that, again, with different mixing, there is a different nutrient supply to the surface, which leads to different primary productivity, and so leads to differences in the CO2 fluxes, which is what is shown here. And there was up to like 40% like changes in the net over the span of a 6-year simulation. So we're really talking about fast changes. And then last example, and this is actually not moving much higher up in the water column and what I'm used to, so I'm not really expert about this, but this was another example where, again, mixing can actually alter pathways of tracers in with very fast timescales. And this is like a combination of really how tracers are supplied in subtropical gyres, which is important to because, I mean, they're not the most productive areas, but I guess they're fast areas, and so we can actually still contribute significantly to transfer of carbon, for example. And so the question is really how much nutrients make their way to the euphotic zone. And the answer, I mean, this is the plots here are taken from Gupta and al. 2022, but there have been more recent papers coming out on this topic, and really the answer is like, well, you need a combination of eddy isopycnal transport. So the eddies, which is shown here, I guess better maybe, but we do transfer like the nutrients along the flank of the jar into the interior, and then it's thanks to the pycnal mixing then that these tracers like make their way to the euphotic zone. Of course, without this isopycnal supply, there will be after a while not much of a gradient. So it's really the combination of the two that keeps like this nutrient like transfer of the way to the again euphotic zone. And then the last, really the last just minutes, I wanted to spend it more on how we actually where we are, I guess, in terms of observing and modeling mixing. As I said, it's a small scale process, so there are many challenges. However, when it comes to observations, I think we start having we know we have different platforms now to locally observe like mixing. This is taken actually from a paper by Arnaud Le Bourrier and Nicole Couto and collaborators, which actually really pushed for turbulent fluxes to be recognized as an essential ocean variables, given the role that really important role they play in both the circulation and tracer distribution. So we start having a number of platforms, and I think there is more push to really also have the turbulence sensors on Argo floats, which will, I mean, of course, allow us to have a much more global coverage. And in general, like, so localized observations are scaling up in space and time. And I want also to mention the importance of trace release experiments. I showed you one, but all of as much as we can scale up this type of observations, but at least for now, still, well, we're scaling up, but still sparse in time and space, and they're especially very localized. So, and this is an intermittent process. So trace release experiments on the other end really give us more information about what's the bulk like mixing felt by a tracer. I'll wrap up very soon. Thank you. I see.
If you could
Thanks.
including comments, that'll be great, just to.
Yes, I just wanted to, yeah, so the main point is like observation, I guess, are scaling up in space and time. The question is really how can we use them to improve our state estimates, which are at the moment still quite a crude representation of mixing. And this will help us also with our numerical models, because as these high resolution models really often nested based on state estimates. And so I guess this is really just a summary of that. I think we're still narrowing the gap. Observation is scaling up in space, numerical models have increased resolutions. And the point is like in terms of linking different communities is that really how and can we push it to ecosystem scale? Like things that Lisa Levy mentioned yesterday, how much mixing is regulated by benthic ecosystems and roughness like created by benthic ecosystems, or the nutrients like supply again in benthic layers. And with that, I'll stop. This is just a visual summary. I'll leave it up there. And thank you so much.
Great, thanks for the talks both. Henri from UCI. I have a question, I guess mostly for Jake, but maybe Laura wants to chime in as well. So it's clear, I think, that steady state inverse models like the TMI and the OSIM that underlied Tim's biological pump analysis and other models like by Samar Kadiwala are really useful for the historical circulation, which is pretty reasonably approximated as steady state with maybe small corrections that are trending. And those small corrections have predictable implications for tracers like the CFCs you showed. And then at the same time, even though they're steady state models, we have these other tools like dynamical data assimilation and state estimation that are useful for the upper ocean and characterizing shorter or faster frequency variability and changes, but they're not equilibrated in the deep ocean and not really trustworthy for the deep. And I'm a bit concerned that neither tool is adequate in the coming decades for what we expect to be leading order changes in the circulation. And yeah, I'm just wondering what can we do about that?
Mm-hmm. Yeah, thanks, Henri. Great question. One way to look at it is that the success up to this point, being able to take anomalies and basically move them around the existing pathways, is saying that we're in a small perturbation state so far for the ocean. So it's as if we were able to linearize the true ocean circulation, allow just these anomalies in the properties to change, but nothing else. And so the question is, when do the small perturbations no longer qualify as small? When that's the case, essentially you have additional terms. You think of a Taylor expansion, if you want to think of it mathematically. So you have a term coming out that's going to be the background state being moved by changes in the circulation. That's the obvious next thing that is at the leading order scale. Then, you'll have combinations of those terms, which I think are, wouldn't be our first thing to go after. So it would be change. The next thing to do, I think, is how background quantities are changed by variable ocean circulation. You get into all sorts of tricky questions, right? Like, do you need a seasonal cycle? Absolutely yes, for certain questions. There's other questions like, what is decadal variability in the ocean? Is that part of our baseline? Or is that something that needs to be explicitly modeled? How big is that really? So the baseline is not really one ocean state or one ocean circulation. It's what is the statistics of the background ocean? We know in geophysics things that are red noise or have a red spectrum in both space and time. And so that would be the better way to define the baseline, but it gets very complicated with a global model. So Laura, did you have thoughts you wanted to chime in?
Sorry, I first need to mute. No, I mean, that's probably much better answer that I could give. I mean, I agree there are difficulties in the tools. I mean, for the state estimates, I don't know, that's maybe it's a sidetrack, but the question was like how we can actually, I mean, maybe Ellen or others in the room and Patrick like can help answer much better, but it's mostly like thinking more really how can we actually improve them and when are we going to be able to include all the amount of observations that we have, right? Because all of the biochemical properties, for example, when we measure them that Jake showed, they can actually tell us a lot already about the oceans as a whole are not included at the moment. And I guess it's mostly a computational cost thing, but I think that would be like a big leap forward in constraining those much better.
Ask a question.
I kind of want to comment on this. I think, do we have any reason to believe that the ocean kind of was in equilibrium, ocean circulation? That's like from yesterday, Gohan talk show the age of the kind of age of the ocean response to perturbation or something. We know that's kind of thousands of years, and over the past like 1,000 years, 2,000 years, that continuously some kind of climate change signal happening in the surface. Basically, you keep forcing the ocean is responding to that. It takes thousands of years to responding to that. Maybe the ocean never really actually in an equilibrium state. So there's no reason we can expect that, right? And for the echo estimate, at least for the deep ocean part, it could be responding to something happened a long time ago, like what you show, right? So it's in a transition state. It could be continuously in a transition state. So when you observe something that shows some kind of trend, it's at least possible. Not necessarily see what's showing echo is right or other reanalysis is right, but at least it's possible. Some kind of transition phase or something like that.
I totally agree. The waters, radiocarbon tells us the waters in the deep ocean can be more than 500 years old, 1,000 years old. The surface climate at that time was, it wasn't the same in 1800 as it was in the year 1000. We have medieval climate anomaly, little ice age, those variations. So what it gets down to is for what purpose, to what level of detail are you trying to detect something? So for example, medieval climate anomaly to little ice age, there's good evidence that mean SST cooled by about 0.3 of a degree. When you put that through a model with ocean mixing is going to damp signals to some degree. Only the very longest term signals will get through unscathed. And the model I have would tell you maybe half the signal would get through or 1/3 of the signal of the medieval climate anomaly to little ice age. So you have a signal on the order of 1/10 of a degree. And does that matter for the problem you're answering? For something like global warming, as we go into the future, that pre-industrial variability will get smaller and smaller relative to current events. But you can imagine unintended or shifts in our understanding due to taking into account pre-industrial variability. So we have a deep ocean that's maybe lost a lot of heat over time, and it takes a very long time for it to come to a new state. So I think the jury's out on how much it will matter.
And I know there's a lot of interest in this, but we really need to shift to our panel discussion. So maybe some of the questions that you have will be ones that we can address as the panel. So if we can get the other two speakers to come up and sit with Jake, we'll have a panel discussion for the next 15 minutes. And I think let's, just like we did with our first panel discussion, really kind of, first of all, let's thank our last two speakers. Hey! And Laura, I'm sending you a virtual hug.
Thank you.
So similar to the last panel, let's really focus on tying things together. I love Laura's talk in thinking about how short-term turbulence can affect long-term circulation. So let's really try to weave across slow and fast pathways and do a little bit of a deep dive. All right, go Ken.
I'll go with the slow pathway, I guess that's right. So this is mostly for Jake, I guess, and I showed it in my presentation as well. When you compared the observations and then the dynamical models, and I think was the reanalysis in between. One thing that occurred to me is that, or just very obvious, is that when you compare those Atlantic sections, in the observations, you do not see any signature of the overflows or any sort of injection at about, I don't know, 1,000 meters, or that was actually, in the observations, everything was going straight down to deep. Yet, when you look at the dynamical models, you can see that intrusion signal. Do you know, is it a problem, or is it an issue with how you do the observational analysis, or is it lacking in the observations, or is I mean, do you have any idea?
This is on. I can be loud, but they might not hear me online. It is on?
Keep talking.
Okay.
Yeah.
Okay, great. Oh, there I am. Gokhan, great question. I think we see that when doing a Nordic seas analysis, it was at about 1/4 of a degree resolution, 1/4 by 1/4 degree. You can really then pick up the bathymetry. You can pick up flow along the Reykjanes Ridge. You can pick up the overflows. All of the analysis or the models as well for the entire Atlantic were at 1 degree resolution. Doesn't seem to be sufficient, I would say.
That's what I'm asking, Magnus.
Well, first, if you use climatologies, for example, often they do not sample within 20 meters of the bottom. And oftentimes you're going to have a dense overflow that might be confined to 20, 30 meters above the bottom. When using TMI, there is a way to say, increase the error in the climatology at the bottom so that you can allow a connection to exist. I think if you make the right plot with this analysis of the observations, you would see something that's like in the model. Taking a zonal average of the Atlantic will not show it. You know, the lateral changes will be blurred out when you look at a zonal average.
Oh, sorry, Isabela has her hand up online.
Hi, thanks all for the great talks. My question is mostly to Laura. Had a comment at the end when she was finishing very quickly that I thought would be great to expand on in this interdisciplinary audience, especially. You were just starting to talk about mixing at the seafloor and the interaction with benthic communities, and I wanted to see if you could expand on that, and maybe some of our other panel members have some thoughts too.
Yes, I mean, I think that discussion actually was initiated through DOOS, like the Deep Ocean Observing System. So we really started talking about, again, linking different communities. But that's one topic that came up. One is really like we start now having high resolution numerical models. Henry can also talk more about this since he's one of the people working with these models. But up to the point that we have good, at least much better resolution, also close to the seafloor. And like the models also Lois Baker used has like over 200 also vertical levels. So we're talking also about models again also in the vertical, they have much better resolutions. And there can be regional, of course, but some of them actually happen to be in regions of interest also for benthic communities. And so again, how can we just simply exchange resources? That was really one thing. And then there was more discussion about really what's the role of like benthic structures in generating, because we know that roughness is really important in generating turbulence. And I guess, again, the new studies, it really shows that it can happen also sharp interfaces, so even more so. That I think it's still kind of an open question. It's like, but again, that could be another really community-like interactions. And the last thing is also, this goes back to Kurt Bolzin actually in WHOI, is like when he deploys like instruments to measure really the turbulence fluxes, they can also have deep cameras, and we do take pictures of the benthic floor. So it's really linking information about what is living down there with what's the turbulence down there. And this is, again, it's just like putting things out that we have been discussing the last few months in terms of, again, resources that could be shared and information. And I think, yes, so if anyone in the community, mostly, the point is like, again, one of the points of this workshop to engage more across communities. And I think that's what we've been trying to do. And I think, again, narrowing the gaps between scaling up observation and having high resolution models, I think we're reaching a point that also biogeochemical and ecosystem benthic ecologists I think we have the tools basically that we're looking for to some extent. I don't know if anyone in the room wants to expand on that, or if I have needs basically that I think the physical oceanographer community basically can do. And one thing is to point out, especially in models, when physical oceanographers, work with them, we don't think about, what's the output that could be useful for the other communities. So it's good to have this conversation beforehand. What outputs would you need at what time and spatial resolutions, and how can basically we collaborate on that.
Awesome. Did any other panelists want to make a comment on this? And Laura, you totally crushed that answer, by the way. Okay, go ahead.
Yeah, DOOS. This is really DOOS led initiative.
I'm far from an expert on benthic taxa, but I think just another thing that's worth starting to think about as we get to these higher resolution models is that understanding the physical motions around all this rough bathymetry is also really important for all the benthic taxa in terms of the way you get dispersal for their larvae. So I think there's a lot of interesting connections that we're just getting to the point of being able to do. So I think there's a lot of possibility there in the near future. And I'm not a benthic ecologist, so don't talk to me about it, but I think there's a lot there.
I can add briefly, for these bottom boundary mesoscale processes, we often enhance model resolution, the vertical grid resolution near the surface. But to resolve bottom boundary mesoscale processes that might have not just mixing, but also vertical velocity, you also need to enhance the vertical resolution near the bottom, which is often, the grid cells can be quite large near the bottom.
Yeah, I had a slightly different type of question. So going back to Dr. Gebbie's TMI method, I was wondering how dependent, right, your method and reconstruction of the water masses is on your observational coverage, which changes over time and in the past versus, right, in the future, presumably, right, the observational coverage is better. And then the follow-up question is also for everybody here, for both your large scale and then for everybody else who works on the smaller scale. In our group one yesterday, we talked a lot about, right, Argo floats and how can we push forward the Argo floats. Maybe you can comment on how, right, increasing Argo float coverage would improve your work. I don't even know if in your TMI matrix you use that at all. So, yeah.
Yeah, absolutely. It would. It's basically built to take any tracers observed at any location. It doesn't have to be a climatology in order to use it in the inverse method. But the problem when you talk about changing observational networks over time is a really severe issue when it comes to figuring out trends, climate relevant trends. And so, basically we have a background structure that has a huge range in temperature, a huge range in salinity. And so, for example, historical hydrographic information, we take kind of on faith that we know when and where it happened, but they didn't have, global positioning satellites. Often they're just making an estimate of the depth that the observation was made based on the amount of line that was let out, which is not all that accurate. So the small changes in the vertical then can appear like trends over time. And so there's no way around it except being extremely careful, trying to figure out what the metadata was in the past. And up to this point, I haven't felt confident that there was a historical data set that could be used, say, the same way as WHOS or GoShip or something like that. It's already been a huge problem just to collect the data from GoShip, collect it during WHOS over the last couple of decades. So I don't think there's an easy answer to your question.
Any other panelists want to comment?
Yes, I can comment. So the global scaling that I showed of the POC flux, that was from from satellite Argo and BGC Argo, and I showed that we have fairly substantial error bars on the POC flux estimate from that, and that error comes largely from the uncertainty in what the POC distribution is subsurface, because that's relying on biogeochemical Argo, but we don't yet have global coverage for that. And so I think that's highlighting the importance of having observations of what is the vertical structure of biogeochemical properties subsurface on a global scale in more distributed regional variability. The other thing I can say is in some of my work, I mean, these fast processes are episodic. They happen on small spatial scales. They also happen on short time scales. But if you have long enough time series, you can, and the sort of right theoretical frameworks to analyze data, you can actually pull out the signatures of these episodic processes, even if you're not fully resolving them, say in high resolution sections or high resolution data. So I guess the point is we need a lot of data either in space or in time to really understand the signatures of these processes.
Maybe we have Zhenfeng has a question.
Okay, first I want to kind of follow Mike and Mara's comments on the mesoscale eddies impact. Actually, there are over the past few years, there are some studies show that mesoscale eddies can directly link surface and the bottom of the ocean, particularly over those mid-ocean regions, like where those hydrothermal wind community exists. And so basically when eddy pass, you're going to see response of a current over mid-ocean ridges, a very strong one, and that can important for the dispersal of everything there, and also generate some mesoscale processes over those regions. So it's a kind of a direct pathway connecting surface and bottom of the ocean. So that's something I want to bring that up. And then another.
I can say briefly, yeah. So that'd be a direct energetic pathway.
Yeah.
Right. So you're not connecting the water mass, but
yeah, no, non-material or
yeah.
something, just signal.
Yeah.
Can connect them together. Yeah. Then I have a question to Laura about the in your talk you mentioned like upwellings a couple of times, and I look at it carefully. And I think there are two different kind of upwellings mentioned there based on the coordinates used. Right, they are upwellings based on the kind of a cross isopicanal. It's a kind of dipicanal upwelling. There are also upwellings on the geopotential coordinate, basically Z coordinate. So I feel that for different community, the usage of those could be very different, right? So for understanding water mass transformation, etc., the dipicanal upwelling is crucial, is important. Those seems very important for physical oceanography. But for people who want to understand the distribution, maybe by geochemical tracers, etc., maybe the upwelling on the geopotential coordinate matter more. I don't know. That's just some thought there. I want to hear your thought about that, and the panel's thought about that kind of thing.
Yeah, thanks for the comment. Yeah, indeed, I think when I talk about upwelling for me, yes, it's cross-like density, and I agree. It does change depending on the community you talk to, and maybe I don't know if it's a good like. Well, the point is like it would be good, I guess, to convene on a language which maybe is less confusing. I don't know if it is something that Henry is going to talk about in terms of the methods or in terms of his water mass transformation, like a framework. So there is like I think more also work to do like to maybe find like convert over like a language on this. But yeah, no, sorry, I don't think I have like I don't know exactly. Well, I don't think I have a good answer for that. Definitely, for all I've talked about and all the upwelling we talked about, I'm talking about the denser to either denser to light or light to dense like transformations of water masses. So it's all the like in isopicanal with like coordinates.
All right, we're gonna go to Henri for our last question, and then we'll have our lightning talks.
Okay, just to quickly follow up on that last point. So there's a couple of really interesting talks or posters at Ocean Sciences that ran global eddy resolving ROMS models, and they found that the Eulerian, so the Z potential vertical velocity, is negative at the bottom, which is the exact opposite sign of what the models that Laura and I have analyzed predict. And so I think there is actually an interesting question about the difference between the diapicanal velocity and the Eulerian, like physical space velocity, and I don't think we fully understand that connection yet. The question I had was for Mara, I think, and maybe Mike wants to comment, is I was struck by the plot, I think it was from Takaya Uchida's work on the iron and carbon. And one of the data points was that I think the GM plus READY very coarse resolution global scale model had almost the exact same ratio as the highest resolution model. And so the optimist in me is wondering if we just need to tune the parameterizations we already have well enough, and that gives us the right answer, or is there some problem with that?
I mean, I think that was a sort of optimistic paper that the parameterizations are to first order capturing some of the key processes and biophysical coupling. I think there are some challenges, which are whether the biophysical feedbacks are being appropriately represented when you do the parameterizations in that way, which is to say, are the vertical gradients correct so that you're fluxing across the right vertical gradients? But yeah, so I think we do know a lot about ocean parameterization and how to parameterize it. We do end up with more free parameters that we can tune. So there may be issues as we try to project that into the future.
Awesome. Let's give another big round of applause for our speakers.
Nice job.
All right. So next up is our virtual poster session. All right.
Hello and welcome to my poster presentation, The Habitat and Biogeochemical Properties of Low Oxygen Adapted Tropical Ocean Phytoplankton. Sluggish circulation, long ventilation times, and high rates of oxygen utilization, such as the Eastern Tropical North Pacific, can cause the presence of an oxygen minimum zone. When this nears the euphotic depth, phytoplankton growth can occur in anoxic waters. This community, community 3 here, is beyond the optical capabilities of satellite remote sensing, found at depths of around 100 meters, and therefore is difficult to monitor at high spatial and temporal resolutions. However, the recent advancements in the autonomous floats has meant that we can begin exploring this community more. In this study, we used biogeochemical Argo float in tandem with a conceptual model to vertically partition the phytoplanktonic communities in the Eastern Tropical North Pacific. In Figure 1, the model is seen to fit the data well, as the black line follows the green data points nicely, encapsulating all communities. Community 1, seen by the red line, it resides in the mixed layer. Community 2, seen by the blue line, is just below the mixed layer, and Community 3, by the yellow line, is below the mixed layer but in anoxic waters. The model is an extension of Bruin et al.'s 2022 two-community model, allowing us to isolate each community, seen here with the red and blue and yellow lines. Isolating these communities allowed the extraction and quantification of integrated net stocks. This is seen here in Figure 2. Figure 2D shows that Community 3 and Community 2 contribute similarly to integrated stocks of chlorophyll A, emphasizing the potential contribution that this community has to biogeochemical cycles. However, seen in Figure 2A, B, and C, the Community 2 and 3 contribute less to integrated particulate backscattering than Community 1. It is thought that this is due to depth-dependent variations in the carbon-chlorophyll A ratio, which is key in determining the photosynthetic rate of this community. The isolation of each community also allowed the extraction of environmental conditions in which they thrive. Found at depths of around 100 meters, Community 3 is adapted to the extremities characterized by the extremely low oxygen, low light, and low temperature, as seen in Figure 3E, 3F, and 3A. Despite these extremities, this community contributes to the net stocks at a similar rate to Community 2, found in the higher temperatures, oxygen, and light levels. This could be a result of Community 3's mechanistic adaptability to supplement their growth in these conditions. It's therefore important for us to fully understand this community and its role in biogeochemical cycles in the oxygen minimum zones as they expand and intensify with climate change, using satellite remote sensing, in situ measurements, and ecosystem models. Thank you for listening to my talk. Please feel free to email me with any questions and scan the QR code for the paper.
Within 2 seconds.
Good evening. Yeah, I am talking about especially bearing biogeochemical parameter estimation in the global ocean model. Next slide, please. The ocean biogeochemical model includes many parameters, the value of which are not precisely known. And these parameters value depend on physical and ecological context. But in practice, in the model, we use them as a constant value or uniform value everywhere. In this study, we estimated spatially and temporally bearing parameter in a biogeochemical model, RECOM 2, using ensemble data simulation. Next, please. So we estimated surface chlorophyll concentration from the satellite, applying an ensemble Kalman filter. we perturbed 9 biogeochemical parameters to generate the ensemble and estimate those parameters together with the model state. Next, please. So here we see the one of the parameters we estimated, the especially bearing value of the estimated parameters. The phytoplankton initial slope of photosynthesis resilience curve. In the bold value shows the initial value we had, and we can see that the value is very especially, and we have checked with the available observation. It's more or less consistent with the observation, the estimated values, and we ran the model with the all estimation, all the estimated parameters. Next slide, please. And here is the Taylor diagram shows the red cross is for the uniform default values, and the blue dot is for the estimated stimulation with estimation, and we can see that the output is far better, and it's closer to the blue observation. And with this system, we can better understand the biogeochemical processes in the global ocean with their variability. Thank you very much.
All right, thank you. Next up.
Oh, can you share the slides, please? All right, okay, sounds good. I'll start then. Okay, so in this poster, I will be discussing about my current research on the variability of oxygen in Denmark 3 overflow water, or DSO, as revealed by moored oxygen sensors in the Erminger Basin. So as you may already know from yesterday and today's talk, Denmark 3 overflow water is formed primarily from deep convection in the Nordic seas and then gets spread southward to the Erminger Basin, where it entrains surrounding water masses in the process. The variability in the DSO hydrographic properties have been studied in the past, but we do not know much about the variability in the biogeochemical properties of the overflow water. So the goal of this poster is to characterize and explain the variability in the oxygen content of DSO from moorings in the Erminger Basin. And in this study, I will be focusing primarily on the bottommost instruments in the OSNAP M1, M2, and M3 moorings, which, as you can see on the center map, sample the western boundary of the Erminger Basin. And you can see in the hydrographic section that the moorings sample the bottom oxygen maximum associated with the overflow water. So one of the key findings of this poster is that for the first time, the OSNAP moorings reveal variability in the oxygen content of DSO over seasonal time scales, which, as you can see on the left-hand set of figures, you can see that over February to July, the dissolved oxygen concentration and saturation increases, and then those variables decrease over July to February during the summer to fall. To gain an understanding of the physical explanation behind the observed variability over seasonal timescales, we performed a water mass decomposition analysis of DSO using 4 end-member source waters. And as you can see on the results on the right-hand figure, you can see that there is a seasonal signature of the percent Northeast Atlantic deep water, which is less oxygenated, and the more oxygenated Labrador seawater, which is shown in blue, which suggests that the seasonality may be coming from the relative contributions of NADW and LSW that participate in entrainment. But the current analysis does not account for any time variability in the end-member source waters. So the next step is to be able to apply an entrainment mixing model to assess the extent to which variability in source overflow properties and entrainment processes influence the variability in the DSO properties observed from the moorings. And that concludes my talk.
Fantastic. Thank you. All right, next up.
Hi, can you hear me?
Yes, I can hear you.
Okay. Can I share my screen or you?
We have your slide up.
Okay. Thank you. I will get started. Hi everyone. Today I'm here to talk about our study on the dynamic of the deep water overflow seasonality in Luzon Strait. Please, next slide. We utilize process-oriented simulation to find out the driving factor behind the deep water overflow seasonality. The model covers the South China Sea and the adjacent Western Pacific Ocean with a horizontal resolution of 3 km and 50 vertical levels. We force the model with climatology wind stress and initialize with horizontal uniform profile. Notably, the vertical turbulence mixing coefficient was from observation and was enhanced in the South China Sea. We prescribe idealized external volume fluxes along the eastern boundary to introduce the western boundary current. Our simulation reproduced the layer circulation in the South China Sea, capturing inflows in the upper and deep layer and outflows in the middle layer. Below 1,500 meters, deep intrusion was induced by contrasting mixing intensity. Validation against marine data confirmed the accuracy of our simulation in capturing the direction and magnitude of the velocity, as indicated by the red arrows. The seasonality was also validated against satellite observation data. Next slide, please. Analyzing the force balance revealed that bottle along isobast pressure gradient force play a crucial role in propelling deep water through the Luzon Strait. In the along isobast direction, the bottom layer pressure gradient force exhibits spatial consistency with deep overflow. Besides, the pressure gradient force is larger than the Coriolis force, indicating most of the pressure gradient force cannot be balanced by the Coriolis force. So, analyzing the mechanism of the pressure gradient force could lead us to understand the deep water overflow. Moving on to the seasonality, we decompose the bottom pressure gradient force into upper, middle, and deep layer to understand their contribution to seasonality. The bar plot illustrates that both the upper and deep layer drive intrusion towards the South China Sea. We also observe consistent seasonal pattern across the upper, deep, and bottom layers. Deep layer oscillation are linked to density difference between the Pacific Ocean and South China Sea, while oscillation in the upper layer are influenced by local wind seasonality and the displacement of the crucial current. In conclusion, our analysis revealed that both barotropic and deep baroclinic signal are crucial in shaping the seasonal pattern of deep water overflow in the Luzon Strait. Thank you for your attention. Any comment or advice would be most appreciated.
Awesome. Thank you so much.
Thank you.
All right, next speaker.
Yes, hello. My name is Elena, and I'm a PhD student in the University of Barcelona, and this work has been been developing the company Lobelia, also in Barcelona, and it's called atmospheric forcing for dense water cascading in the northwestern Mediterranean. So this is our area of study, where dense water overflow happen in winter, in some winters when the winds from the north and northwest cool down the shallow water. And then it sinks through the submarine canyons, mainly this, well, I don't know if you can see it in here in the arrow, the submarine canyon of Catacres Canyon. And when the shelf density is very high, it cascades down. There are some observations, but very few because this happened when the weather. I use a reanalysis product in here to try to study all these dense water cascading events that have happened in the last decades, and also try to induce why they happen those winters, what were the atmospheric conditions that trigger that shelf water to be so dense and to get those dense water cascading events. Can you please pass the slide, please? Yes, thank you. So these are some of the observations of a mooring line. And here, next slide, please. Well, next, please. So our analysis product to see the previous cascading events previous to the observations. Yes, like this. Thank you. And next, please. So we get more than 30 years of a time series with the cascading events, and these are validated with the observations. So what we do here is try to induce what was the atmospheric forcing for those cascading events when the shelf water was denser than the deep water. And the atmospheric forcing for that reanalysis is R5. So we calculate the RC fluxes, and we also see the correlation with a large scale atmospheric pattern, that is the East Atlantic atmospheric pattern in a negative phase that induces cold air and stronger winds. And that's it. And if you have any questions and so, please contact me at my email. That is in the first slide. Sorry. Thank you. Thank you so much.
Great, thank you. All right, next speaker.
Hi everyone, my name is Matilda and I'm a postdoc in Seth Bushinsky's lab at the University of Hawaii at Manoa. And this poster presents some preliminary work in which we are following the evolution of biogeochemical variables along ventilation pathways based on observations, more specifically on the Argo floats, and we focus on mold waters. So here you can see kind of an example for the Pacific subarctic mold waters for a given density layer. And the red lines on the figure are showing the streamlines, and they're based on the geostrophic velocities derived from core Argo. And so from that, we get like a 3D ventilation pathway based on observations. And then we find all the Argo BGC data that fits within that, which are all the little points. And we can follow along the pathways how the waters evolve. And this is what we see on the middle panel on a TO2 diagram. So if we move, and yeah, the colors, so if we go from dark to yellowish, it means that we're moving along the pathway. So we can see that temperature is increasing and oxygen is decreasing. But as you can see on the little schematic on the right, if we had only biology changing the properties, we would expect to only have a change in oxygen. And so from the change in temperature, we can retrieve what is the amount of mixing that occurred between that water mass and the surrounding water masses. And by solving the mixing equations along the pathway, we can get the percentage of the change in any biogeochemical variable that is due to mixing and not to biology. You can change the slide, please. And what we find is that mixing contributes to more than half of the changes that we observe in the biogeochemical variables. So by that, I mean here oxygen and nitrate throughout a range of different water masses. And this has implications for people who use, for example, AOU or the difference to preform nitrate, because it will overestimate biological activity. So please come and see the poster for more details. You can find it on the virtual gallery online. And also, please feel free to email me to know a bit more and to have a discussion. Thank you.
Thank you. And y'all did not want to stop that earlier panel discussion. So if anyone has any last loopbacks that they want to talk about, raise your hand. We'll get you a mic and we can kind of chit chat a little bit more, and then we'll head out to lunch. Sorry, the Tennessee came out there.
Yeah, just related to what you and I were talking about earlier, and that may be a question for all of the speakers. We were talking about places where we might learn new things, like hotspots for those pathways, and like we know some of the overturning hotspots where the deep water formations are formed. But now it sounds like there's the mixing over topography, and like there's also the subduction that happened at France, and there's also some places where maybe we know better than others about what the BGC Trump is doing. And so we were wondering if there are some places in the world that we benefit from more knowledge and more data, if anybody has thoughts on that.
Like it. Oh, Lynn.
I was just going to say, circling back to the various scales of overturning and what deep means, and possibly in response to Gokhan earlier. So as a physical oceanographer, we're talking abyssal. So, and then we talk about the ventilated thermocline, and I think we haven't talked much in that framework here, but that is super important locally, and the time scales are just 10 years or so, and that gets into what's considered deep ocean for the biologists. Just a thought. that we haven't separated those in the physical side.
Yeah, Jinping, would you mind running the mics?
I guess responding directly to Lynn, I think the processes that I was talking about are mostly those ventilated thermocline. And I guess I'll try to respond to Monica. I think you can make the case for many places in the ocean. I would say that one that we haven't touched on as much in this workshop is equatorial regions that are both high primary productivity and so we think relatively high sinking export. And so that was why in the plots that I showed, they showed up as relatively less important for mixing fluxes, but the sort of mid-latitude scalings that we use don't necessarily apply in the equatorial regions. And so I think that's an area of knowledge gap.
Yeah. So I'm always biased towards the Southern Ocean, so I would always say more, more Southern Ocean. But I don't know that we have Arctic representation here, right? And the problem with the Arctic that we know is that there are no Argo floats that go to the Arctic. So in some sense, gradually over time, the Arctic may be left behind the Southern Ocean.
Will it? Oh, Argo's going to Arctic next year? Oh. Yay!
So I guess, yeah, for Lynn, what happens with the Argo floats once they get there? They just disappear?
I think Norwegians are already putting them in. I mean, if you look up in the Barents Sea and on shelves, you'll see them already. And that's something. Oops, here we go.
We talk about this. There are various programs for developing technology. We'll be able to put the BGC Argo in places that are seasonal sea ice by next year, not this year. We just have to put ice avoidance software on on the Scripps floats. The brand new Scripps BGC floats will be able to pierce. The problem with Argo is the halocline density contrast is so high to be able to ballast the floats so that they can actually get through the surface layer to the surface and talk to satellites is hard. Scripps floats will do that. They don't have ice avoidance yet, but they will next year.
Is that, and that's just in the Arctic?
I'm just talking about the Arctic.
Yeah. No, the problem is it's less of a problem in the Southern Ocean than
Much less of a problem. Yeah, that density difference is just ridiculous in the Arctic. So talking about the Beaufort Sea, Chukchi, impossible for the Apex and Navis floats, but for there will be no Navis floats as of next year. They're going out of business on making floats. But there'll be Apex and Solo too. Yeah, Apex can barely do it in the tropics is the hardest part for the global Argo because of the density contrast from the deep to the surface. That is a really good question. And so it's really important to push in that direction and for getting floats and ways to sample under all of the ice in the Arctic.
Yeah, I guess it's a problem in light of the current war because now with less Russian, right, scientists and less communication with the Russians and so forth, right? The fear is that Arctic oceanography will just be impacted because of the war indirectly.
Well, Ghost Ship is going from Tromsø to Bering Strait in August on the Coast Guard icebreaker, and we are deploying some German Argo floats on the way. Yep.
I just heard about a new program with some new tech going in the Arctic at the Decade Conference. Forgetting what it is, but it's like basically it's just going to be stuck in the ice and kind of float around. What's that? Yeah. Super cool. Would not want to be on that expedition. They're looking for volunteers. All right, guys. Lunchtime.